Okay, we're ready to restart. We have seen Little's formula, which is really the great hit in queuing theory. So this is the most useful, probably, formula, although you've seen it's very simple. Let's see, for example, a use of this formula to obtain what is called the utilization law. Consider a queuing system that is made of a buffer and a server that handles the job. For example, that's a single processor, a single core machine, or a communication link here. Little's formula can be applied to any system. We just need to define what is the boundary at the input and the output, and anything in between gives you number of customers and response time. Here, I can apply it to just the server. Not the entire system, but just the server here. So if I consider the server, then the residence time is called the service time. It's the time spent by a job when it's really being handled by the processor. So it's called the service time in a queuing system. The average, if there is a single server here, one server, the average number of customers, well, it's the average of something that is 0 or 1. So it is the proportion of time where it is 0 times 0 plus the proportion of time where it is non-zero multiplied by 1. Non-zero, the server is non-zero, is the same as the queue is non-empty. If we consider a single server queue, whenever it's impossible to have somebody waiting and the server is idle, at least in this simple model of a single server queue, right, which is work conserving. So if we apply this, we obtain the formula, the rate at which jobs arrive. Now the rate at which jobs arrive into the queue, if the system is stationary, should be equal to the rate at which they exit the queue and enter the server. That's where the stationary assumption has to be assumed for Little's law. Right? Over a very long simulation, of course, there will be always one or two things at the end, as we discussed, but if we ignore those little rounding problems, over a very long period of time, the number in is equal to the number out. Otherwise, it means we are exactly in the non-stationary simulation case. So this is the same lambda. So lambda times S, which is the service time, is equal to this, and this is the proportion of time, which is traditionally interpreted as a probability that the queue is non-empty. Right? So we have a first queuing theorem that says that the utilization multiplied by the service time for a single server queue is equal to the probability that the queue is non-empty. In particular, it should be between 0 and 1. Right? Which means that gives you a necessary condition for a stable queuing system. Lambda S should be less than or equal to 1 in the worst case here. It's also a very useful quantity. Lambda S is interpreted as the utilization factor of the server. Is the fraction of time that the server is busy, is occupied. When we reason about complex systems, that's an important figure of merit. If a part of a complex subsystem has a utilization that's very close to 1, it is traditionally called a bottleneck for this system. That means that's the thing that is limiting the performance because you cannot use it more. Right? If a part of your system has utilization equal to 0.001, that means it's not at all a bottleneck. You can improve it. You can, if you think of Lab 1, one of the key things that Joe had to do to know what to improve in his wireless access shop was to find utilization factors. If the utilization factor of the wireless LAN was close to 100%, then it was the bottleneck. Right? So we see it. We can capture this with this simple number here. I will just show now a very commonly used model that can explain many, many practical situations where we just combine all the little things we have seen so far. The little in the sense of little formula, little in the sense of complexity, but great in the sense of their implication. Very often you can model a system with a closed loop here. For example, this is called the interactive user model. This is, for example, what happens when you have a number of customers that are working on a data center. and you have a fixed population of users here. And the users are either what we call here in think time, or they are using the data center or the service center. So a request or a job enters the service center. The service center may be a single queue or a multiprocessor machine. There can be multiple things handled one at a time. There's no assumption made here. All these operational laws that I'm giving, Little's formula, whatever, they are completely general. They apply to any type of delay system, not just a single queue. And then I'm interested in quantifying a relationship between different quantities. So if I have a closed system like this with n users, the population n is fixed, the figure that is an interesting figure is now the rate of transactions. Now the rate of transaction is not an input parameter in such a system, it's an output parameter. If I have a system like this that is very congested means users are always busy doing something here. Then lambda will not be the same as if the system is not at all congested. Not at all congestion means the service is very fast, so I put a request, very quickly I have an answer, then I can do my own thing, which is thinking perhaps, or reading, or doing local computations. So if the system is not congested, most of the time we are here. And therefore, since those timings are dependent on the emerging properties of the global system, it's not easy to predict what is the value of lambda. In fact, lambda is an output value, and we would like to be able to relate it to other quantities. A quantity of interest is, for example, z, which is the time spent in the first part of the system, and r in the second part of the system. Now, if I apply Little's formula to this system, so in fact, I apply it from A to B. Now, A is the same as B in reality, because here, when a customer leaves the service center, it immediately comes to the think time. But to make it less ambiguous, I consider them as 2 points. If I apply Little's formula to this, what do I obtain? What is the average response time? Well, the customer spends here some average time Z plus some average time R. So Z bar plus R bar. I put the bars for averages here. Multiplied by the lambda. Now we should have the same lambda in here and there. So multiplied by lambda is equal to the average population in this part of the system between A and B. But since the population is constant equal to n, the average is also n. So this is equal to n. That is a first relation that I obtained simply by applying Little's law. So it tells us that if I'm able to measure the average think time, the average response time of the service center, and then there is lambda will be n over z bar plus r bar. I will know exactly this number here. Okay, not so surprising. Now let's do the other way around. Assuming this is now a car rental company in an airport that has 10 service attendants. So now the users are the service attendants. Every attendant prepares transaction on its PC. So if you rented a car in an airport, it's irritating because you always have those people that are supposed to serve you, but they're working on the PC because the inputting the transaction is very complicated, so they are not available for you. And once a job is completed on the PC, you send it to a database server. So the service center, here is a database server here. There's a software monitor that finds the following averages. There's one transaction every 5 seconds, and the response time of the software monitor here of R, so of the database here, is 2 seconds. Now we would like to know how good our employees are doing. So what is the average think time? Now it's not the think time, it's the average time spent by a transaction being handled by one of the clerks here. What is are you able to find that? Do we have enough information? And if so, what is the value? unanimity on answer E here, which is the correct one if you have a calculator, or if you're able to do a bit of mental computation. So if we apply the formula here, we find 1 over 5, that's the rate measured by the monitor, times z bar plus 2 is equal to 10. So if that gives you z bar equal to 48 seconds here. Right. Okay, that was very easy. If we combine that with another thing called the network laws, it has a big name, but it's something also very simple, which says that if I have now a network where jobs move from place to place, then I can have a rate, lambda k, which is not the same everywhere. For example, a job can come here and visit something many, many times. So if a job comes in and does 10 rounds here, then this lambda k will be larger than the lambda here. Right? So this is captured by assuming we know lambda k here. Then we have, by this lambda k. And what I said here informally is what this first law is expressing. If we do 10 visits per round here, then lambda k will be 10 times lambda. Right? So if vk is the average number of visits to node k by an arbitrary customer during the stay in the network, then lambda k is equal to the rate of arrival of customers multiplied by the rate of visits. Right? It looks obvious and simple, but that's again very useful. And the total response time, if a job comes in, visit a number of things, so that's you when you do go shopping in the supermarket, right? Visit a number of things, and you go to buy some banana, then you think, oh, but I forgot some salad, so you come back. So in average, you visit a part of the store 2 or 3 times. Then the average response time is equal to the average response time, the sum of the average response time at every node in the network multiplied by the average number of times you visit the node here. Again, it seems obvious, but when you have formulas about averages and product of averages, things are not always so obvious, because averaging is, as we say, can be a bit misleading. But here, we are certain they are true. If you have a doubt, then you do a simulation. You say, if I count this in a simulation, how would I count it? We did this for Little's formula. So if you do this similar exercise, how would you count this in a simulation? Look at all the events or put counters and look at the relation you would have between the counters, and then you will find that there is equality here, if you have a doubt about the equality of averages here. Okay. For example, here is a typical model of, let's say, an embedded processor that has a single CPU. I assume I have a number of tasks that arrive. When the task arrives, or here, no, this is a database server. When a task arrives, it accesses the CPU, the disk, and another disk here. And statistics are that the number of average visits to the CPU by a task is 102, to the disk A 30, to disk B 68. The average response time of the CPU is that number, etc. What's the average response time for a transaction? Then, well, we simply compute all those numbers. What is the average number of visits? What is the rate of visits of jobs visiting the CPU? Well, it's lambda multiplied by 102 here, and the same for disk A and disk B. And then the average response time will be obtained by that. So if I monitor simply response times by locally, and if I monitor the number of visits, I will have some global statistics without having to timestamp a request here until its end, right? This is what this can be used for. But that's not the main interest for us. The main interest is to do quick and dirty, or quick but not dirty, quick and asymptotically exact analysis of a large class of queuing system. This has a name, it's called bottleneck analysis. So people have written books on that. And it's based on putting together all the things we've done. For example, if I have this system and I would like to ask things like, what is the throughput? How many transactions per second can this system sustain here? Right. Bottleneck analysis is not giving an exact answer in all cases, but it will give a good enough answer because it's able to be good at two ends of the spectrum. The two ends of the spectrum is when there is low utilization of the resources and when there is high utilization of the resources. For such systems, when there is very low utilization of the resources, there is practically no queuing. So the response time can be approximated by the service time. When there is very large utilization, there's lots of queuing and we don't know how much time you spend, but there is another thing we will know, that is the utilization of the resource. The CPU cannot be used more than 100% of the time. If the system is close to congestion, we can approximate its utilization by 100%. And by Little's law, we can link those quantities. We can link utilization, lambda, response time, since if we have some information on one, we can have information on the other. That's the program of bottleneck analysis. So let's do it concretely for this example here, for exactly this one here. We have seen Little's formula. That's an example of an interactive user model where we have the think time here, and then we have something which was shown as a black box before. Now I've opened the cover of the black box. It's an entire queuing network, but the same is true. If I call R the response time in this system here, I have lambda z bar plus r bar is equal to n, where n is the number of jobs here. Right. So also I know r bar is this thing here. That's the forced flows and the network flow formula. So I have here an exact formula for lambda. Now to know more, I would need to know what is exactly the response time of the CPU, which is now a queuing problem. I need to know, depending on the scheduler, how the CPU works, what is the response time, given that jobs might be waiting here. So that's inherently a difficult problem, except if we can model the CPU by a simple queue that we will see a bit later. However, we can say that the response time is certainly less than, certainly at least as much as the service time. The service time of the CPU is something that depends on the job itself, not on the population that's around. So it's something I assume I know in this example. Right? So since this is larger than that and it's in the denominator, that means lambda is less than this. This is my first inequality where I've expressed that the response time can be approximated by the service time, but I have more than approximation, I have a bound. So I have this first inequality, and we expect this to be close to equality when the system is very lightly loaded, which would mean here if n is very small. If I have a reasonable system that can handle hundreds of thousands of jobs, and if n is 10, probably it's very lightly loaded. There's quasi no queuing anywhere. So this formula should be close to exact when n is very small. Then the second thing I can say is that lambda, if I look at the three resources, CPU, A, and B, the lambda CPU is equal to lambda multiplied by the number of visits to the CPU, which I've measured is 102. So therefore, 102 times lambda times the average service time at the CPU, and this is called the utilization law. Now the lambda of the CPU is 102 lambda, and this is the utilization law. This must be less than or equal to 1. And it will be equal to 1 if the CPU is the bottleneck and is fully utilized here. But the same happens for the disk A and for the disk B. So lambda satisfies three inequality, and it must satisfy the three of them together, which means that lambda is less than the minimum of those three things. The inverse, 1 over 102 lambda, etc., 1 over 2 S bar CPU, etc. So lambda is less than the 3, means it's less than the smaller of the 3. So I have two inequalities, and I expect two also to be true with equality. So lambda should be equal to the mean of those three things if the system is completely congested, if n is huge compared to the expected dimensioning of the system. So let me plot what this means. if I plot on the x-axis n, on the y-axis lambda, the throughput here, I can plot the first inequality. That gives me a straight line, which is this black line here. I can also plot this second inequality. That gives me a horizontal line. I have to plot the different values that are here. And it turns out that the smaller is the one of the CPU. So it will be a second bound here. So what do I know about lambda? I don't know much, but I know that if n is very small, it should be here. And if n is very large, and I would add the system is well behaved, this should be equal here. We have seen in the first week that there is a pattern of non-monotonicity in many systems. If the system is not especially engineered to avoid congestion collapse, it might have congestion collapse. If there is congestion collapse, that means the true throughput would probably be something like this, which we have seen occurs due to various reasons. If the system is well engineered and is avoiding congestion collapse, this will be an exact bound and it will be here. So this is what we can do with this thing here. So you've seen I've used only calculator type of formulas. I'm not using MM1 Markov chain analysis of queuing system or whatever. Those are all very simple formulas that you should know, you should master them because they can be done in 5 minutes once you know them. And they will tell you this point, and if there is no congestion collapse at that point. So if you have a system without congestion collapse, perhaps doing one simulation to find the value here gives you 3 points. That is probably good enough to do an approximation. It also tells us something else. It tells us in this case that the bottleneck is the CPU and not disk A, because there's no way I could go to loading disk A 100%. So my bottleneck is the CPU here. Joe would have loved to see this analysis in the first homework if we would be able to measure everything and have an inside analytical model of the system by knowing what happens to the number of servers, whether the number of access points is a bottleneck. That corresponds to exactly what we're doing here. Voilà, so that concludes the first part of this queuing, not the lecture today, but the first part, which is the use of very simple things called the operational laws, which I call the physics of queuing system. They give relationship between physical quantities, and we have seen how simply by using them in this interactive user model, we can already have a large number of ideas about our system. Of course, if we want a more detailed analysis, we need to use the stochastic model of queuing system, which is now what we will talk about. But even when we go stochastic, there is a first figure of merit, which is stability. So here I'm considering a single server queue. So a single server queue is the simplest of all queuing systems, where jobs arrive. And according to some policy, as soon as the server is idle, it will pick a job and keep it for the time dictated by the requirement of the job. And as soon as this is finished, the server will pick another job to serve if there is one in the queue. If there is not in the queue, the server becomes idle. But what is forbidden here is that the server does nothing, is idle, when there is a job in the queue. So this is the simplest queuing system. And single server means that only one job is having his work done at a time here. Then a figure of merit for such a single server queue is the utilization factor, which I call lambda, which I call rho here, lambda times the average service time. We have seen by the utilization law that if there is a stationary regime to such a queue, rho must be less than or equal to 1. Right. In fact, we have a stronger result, which is called Loyne's theorem, that says if whatever the scheduling policy, whatever the distribution of the time, whatever everything, except the fact that there exists an average service time. So here I'm assuming when a job arrives, it will have to spend some amount of time which is random, which might depend on lots of things. It might depend on a random choice done by the job. It may depend even on the size of the queue or whatever. But if in average if it has an average that we can compute, so it's not a distribution that has an infinite average. There exists some. We will see the Pareto distributions, for example, that have that. If that average exists, multiplied by lambda, the arrival rate here, if the row is less than 1, then this queue has a stationary regime and converges to it, right? Which is expected, right? This is what you said a few minutes ago. If you have a queuing system where row is larger than 1, this will not happen, so the queue will overflow. But this is a positive statement. It says if row is less than 1, there will be a stationary regime, which means you can do a simulation, remove the transient part, and you can take measurements that will give me what happens in the stationary regime. So this is a complicated theorem. We will not look at the proof. It's very evolved in terms of stochastic processes. The interesting thing is if rho equal 1, the theorem says nothing. So this is the critical value, and it's very typical of queuing systems. At the critical value, we expect things to be unstable, but you can have special systems that are stable at rho equal 1. And here again, I stress, this is very general. It does not assume independence of anything anywhere. That's a very general result here. In practice, we use this result for simpler queuing systems. So here is the perhaps most widespread and mostly used queuing system. Queuing system terminology uses things like MGI1, sometimes with more things. So MGI1 means the first letter represents the arrival process. The second letter represents the service process. The third letter or digit represents the number of servers. And if we need more information, there is a fourth or a fifth information here. So M stands for Poisson. Markov, in fact, it stands for Markov, but what it means is Poisson arrival process. What is a Poisson arrival process? Qualitatively, intuitively, or mathematically, either way, what is it? Yes?
I think it's when you have a high ability to arrive at the beginning at a low value, and then the more time you go, less likely it is to happen at last time, but the more likely it is to happen.
No, that's exactly the opposite. Okay, so the Poisson arrival process is the most random process you can imagine if you know only one thing, the intensity, lambda. So imagine there are 2 customers per second, and it's random. And you don't want to assume anything about other than that. There are 2 customers per second. So the maximum entropy process that corresponds to 2 customers of arrival per second is the Poisson process. Now, mathematically, how do you realize it? The true or one mathematical representation consists in saying you draw according to an exponential random variable with parameter lambda, exactly the same lambda. You draw the time of the first arrival. So you do a simulation with the random. We've seen how to do that last week. How do you simulate an exponential random variable? If I give you a random number generator, minus log of the random number generator, right? So I give you a random number generator, minus log of this, divided by lambda, that will give you a time that by the inverse CDF principle is exactly a sample of the exponential distribution. It gives me my first arrival. Then you draw it again, that's starting from this time, that will give you the second, and you continue. If you do that, you'll have a Poisson arrival process. That's the mathematical construction, but it's not very helpful. It doesn't say why you do that. Why do you do exponential, not Gaussian, not Pareto, not whatever. And there's a reason for that. It's the memoryless property of the exponential random variable, which I interpret in a different way by saying, imagine we are at the time scale of picoseconds. Right? Every picosecond, I flip a coin, a biased coin, that with probability lambda multiplied by 1 picosecond. So if lambda is 2 arrivals per second, a pico is how much already? 10 to the minus 12. Yeah. So 2 times 10 to the minus 12 will decide now there is an arrival. Since my picosecond is so small, I don't need to worry whether it's at the beginning of my picosecond or at the end. So I'm being relaxed about that. So every picosecond, I flip a coin, and with a probability which is equal to lambda multiplied by the interval of my picosecond, that's the probability that my coin returns yes, there is an arrival. So of course, most of the time it will say no, because this probability is astronomically small, but non-zero. So once in a while, the coin will return yes, there is an arrival now. Of course, in 1 second, there's 10 to the 12 picoseconds, so in average there will be 0.5 arrivals per second, which corresponds to the fact that there's an arrival every 2 seconds in average for my... So sorry, 2 arrivals per second. Lambda equal 2, so that means in average there will be 2 arrivals per second, not 0.5. Sorry. And then I flip a coin, and at the next picosecond, I do the experiment again, ignoring completely what has happened before. So that is memoryless. The fact that there was an arrival now will not have any influence on whether there will be an arrival the next picosecond. So it's possible that there are 2 arrivals in 2 consecutive picoseconds. It's possible, but of course the probability that that happens, the probability that there is 1 arrival in a picosecond is already astronomically small. It's 2 times 10 to the minus 12. So in 2 consecutive, that's 4 10 to the minus 24. So it's extremely even rarer. So that's very unlikely to occur, but it may occur. That's the way to reason about the Poisson arrival process. Every dt, where dt is an infinitely small amount of time, with probability lambda dt, there is an arrival. And with probability 1 minus lambda dt, there is no arrival. And every dt, you redo the thing independently. So it's completely memoryless. If the only thing you know about your arrival process, that's the most reasonable thing to do. There is no specific structure. There's no reason that an arrival occurs here rather than now. You don't know anything about the correlation. So that's the most random arrival process. It is also used because it's mathematically very tractable. If we do analysis of a queue that has Poisson arrival process, the analysis is tractable. GI stands for general, independent. G for general, I independent. I is often forgotten. Very often we will write MG1. If that's the case, probably it means MGI1. Independent means 1. Means that this is a queue where customers are arriving according to the Poisson process with a known rate. And when so the customers queue until their time to be served comes. And when their time to be served comes, they draw from a certain distribution that is known how much service they require. So for this, we need to have a distribution, a probability density function or a CDF or whatever for the time, the service requirement. And the I means it's independent. When we draw this service requirement, we do that independently of everything else, which means we do a call to the random number generator. We apply f minus 1, where f is the CDF of the distribution of the service time, and that tells us how much time this customer will stay in the queue, will stay in service. So this is how we can simulate an MGI 1 queue. And 1 means there's only 1 server. If I had a 2, that would mean there would be 2 servers, which means 2 customers can be served in parallel. For this system, we know practically everything, at least numerically for most of it, and in closed form for averages here. So for example, the average number of customers in the queue is given by this formula. This formula involves rho, so which is rho is equal to lambda times S bar, where S bar is the average of the service time distribution. That's the classical number. We know if rho is for less than 1 is stable, but this we knew already. That's true for practically any queue, any single server queue, or any single queue, in fact. And then the second element that plays a role here is kappa. Kappa is given by this. This is 1/2 1 plus sigma s square. This is the variance of the service time. And S bar is the average service time. So sigma over S, we already gave a name to that, so that's the coefficient of variation. If I have a positive random variable, the figure of merit for its variability is its standard deviation divided by the mean. If it's 0, that means the distribution is constant. Sigma is 0, the service times are exactly always the same. That's a special case of this. If it's a Gaussian distribution, then sigma is the sigma of which is the parameter of the Gaussian distribution. So if we take this quantity, so the square of the coefficient of variation, we see that it appears in the average number of customers here. Using Little's formula, we can have the average response time, so this is deduced by that. We can have also the average number of customers in the waiting room, so including the ones in service. How could we obtain that? How can we derive that from the other? So obtaining this is the so-called Polacek-Khinchin formula. So it requires several hours of explanations and reading of stochastic process analysis. But going from this to this is immediate. So the waiting room, so I have a queue, right? The waiting room is the customers that are here, the ones that are not in service. I know what is the average number of customers in total in the system, but I know also the average number of customers in service. This is the utilization law. It's rho times lambda. So this is the average number in the queue minus the average number of customers in service, because the sum of the averages is the average of the sum. So if I take this minus rho, then I obtain exactly the average number in the waiting room. Therefore, I can have also the average waiting time, which is the average time spent in the waiting room, in this form or another. Here. What do we see in those formulas, apart from the fact that they have closed form? We see that the average, in terms of average performance, it depends first on rho, then on kappa. Right? The dependency on rho is dramatic because there is rho square over 1 minus rho, which means when rho goes to 1, this goes to infinity, which is expected because we know when rho will be larger than 1, the system is unstable, the queue will build up forever. So if rho is just a little below 1, we expect that it is stationary, but the queue will be very large, at least roughly speaking, if we assume there is some kind of continuity in thinking here. This is what happens. So that's the first thing. And this is for all the queues we will see, when the utilization of the resources, if there is a single server, it's rho. When it goes to 1, the queue average performance metrics will go to infinity. There's something else we see, the role of kappa. What does it tell us?
So then we have more variance, so we need larger queue.
When there is more variance, we need
Large queue.
large queue, exactly. So the same queue with the same average, but with more variance, will mean, in average, more waiting time. Right? The service time is the same. The service time is the S bar, right? It's not influenced by the variance. But the waiting time is influenced directly by the variance of the service time. So that's the qualitative take-home message from the Polacek-Khinchin formula. If you have a single queue and there is large variability in the service time, that has an impact on the average waiting time experienced by customers. So if you want to reduce the average waiting time, it's better to find ways through scheduling or through some other mechanisms to make sure that the service time is not very variable. There is a price to pay for variability, which is something we see in all stochastic systems, right? If the price of something is very variable, you need some reserve for just to be able to, I mean, if your price of electricity or your price of your rental is very variable, you need to save a bit of money just in case the rental will be very high. So there's always a price to pay for variability, and here we see it here in this formula. In this formula here, I just mentioned if we if we compare the average number of customers in the waiting room and the average number in the waiting room, which is here, the average number of customers that are in the queue, we see that the difference is just the first is equal to the second plus rho, right? So it's true for this queue. Is it true in general? The majority thinks B, which is very safe, but you can be a bit bold here. The truth is C. Why is it? Well, because of the utilization laws we saw before, right? The utilization law, which is nothing else than Little's formula, if I have any arbitrary single server queue, which must be stable and must have a stationary regime. So that's the only condition we want, so that the lambda here is the same as the lambda. And then I can apply Little's formula. For this, I need stability. Then the average number here is rho. Whether the Poisson or not Poisson assumption holds at the input. So this is quite general. Okay, I think we will stop here for today. So what we have seen is a number of general rules, and we've started diving into some of the explicit formulas. Next week we'll go more into, tomorrow we'll go more into the explicit formulas and see how we can combine the two.